Let us start by framing what this week is all about. Week 10, Introduction to Anomaly and Outlier Detection. Welcome to Week 10. This week, we dive into the world of anomaly and outlier detection in data mining. Anomalies are data points that do not fit the expected pattern or behavior. Detecting anomalies can help you find fraud, rare events, or errors in data. We will use the credit card fraud dataset for hands-on learning. Running the cell now. Think of a real-world problem where you might spot something odd in data. Let us set up our dataset before we get started. We download the credit card fraud dataset. We turn off any warnings to keep the notebook tidy. We import pandas to work with data. Import numpy as np. We set the random seed to 42 for reproducibility. We set the URL for the dataset. We load the dataset into a pandas data frame. We print the shape to see how many rows and columns there are. We display the first 3 rows as a quick sample. Running the cell now. Here, we load the credit card fraud dataset containing 284,807 transactions and 31 features, including anonymized principal components labeled V1 to V28, along with time, amount, and the class label indicating fraud. Notice the balanced structure of the data, which is key as a foundation for exploring anomalies, those rare class equals 1 fraud cases, in later lessons. This setup primes us to understand normal versus anomalous transaction patterns. What do you notice about the dataset size or sample so far? Let us explore what an anomaly means in simple terms. What is an anomaly? An anomaly, or outlier, is any item in your data that is different from most other items. For example, a credit card purchase of $10,000 when most are below $200 may be an anomaly. Finding these helps stop fraud or detect data errors. Running the cell now. Can you think of an unusual event in your own spending habits? Let us get a feeling for our data by looking at its structure and some statistics. We provide a basic summary of the dataset to understand its structure. We display information about the data frame, including data types and non-null counts. We show basic statistical measures such as mean, minimum, and maximum for each column. Running the cell now. This output shows a basic summary of the dataset with 284,807 entries and 31 columns, all fully populated with no missing values. The .describe statistics help us understand the range and distribution of each variable, which is crucial for spotting anomalies, values that deviate significantly from the typical range or trend in these key columns. This foundational step sets the stage for identifying outliers by highlighting what normal looks like in the data. What columns do you think might help spot strange behavior? It is good to check if there are any missing values before analysis. We look for missing values in the dataset. We calculate the total number of missing values by summing over all columns and rows. We print out the total count of missing values found. Running the cell now. This output shows that there are no missing values in the dataset, which means every data point is complete and available for analysis. In the context of detecting anomalies, this is important because missing data can distort insights or hide unusual patterns. Confirming 0 missing values ensures the anomaly detection process is based on a clean, reliable dataset. Try changing the code to display missing values by each column. Our target column is class, where 1 means fraud and 0 means normal. This line explains that we are checking the balance between fraud and normal transactions in the dataset. This line prints the count of each class, fraudulent and normal, present in the class column of the data frame. Running the cell now. This output shows the class distribution of transactions, with 284,315 labeled as normal, 0, and only 492 as fraud, 1. Notice the severe imbalance. Fraud cases are extremely rare compared to normal ones, which highlights why these fraud instances can be considered anomalies in the dataset. This imbalance is key to understanding the challenge of detecting outliers in real-world data. Do you notice if there are a lot more normal than fraud cases? Let us compare the amounts for normal and fraudulent transactions visually. We add a comment describing the purpose of the visualization. We import Matplotlib's pyplot module to create plots. We create a histogram of transaction amounts for normal transactions, class 0. We create a histogram of transaction amounts for fraudulent transactions, class 1, on the same plot. We add a legend to distinguish between normal and fraud transaction distributions. We label the x-axis as transaction amounts for clarity. We label the y-axis as account to indicate frequency of transactions. We set the title of the plot to describe what is being shown. We display the plot so it appears in the output. Running the cell now. This histogram shows the distribution of transaction amounts for normal, class 0, and fraudulent, class 1, transactions. Notice that most normal transactions cluster at lower amounts, while fraud transactions are fewer but spread unevenly, sometimes at higher amounts, highlighting potential anomalies. This visualization helps us understand how fraud may stand out based on transaction size, reinforcing the concept of anomalies as data points that differ from the norm. Practice: try changing the number of bins to see the effect on the chart. Let us talk about why anomaly detection is needed. Why do we need anomaly detection? Sometimes, problems are hard to spot if we only look at a summary or average. Anomalies can tell us about system errors, fraud, or rare healthy events. We use detection methods to find these cases automatically. Running the cell now. What could go wrong if you ignored outliers in a business report? Let us see if fraudulent transactions look different in time and amount. This is a comment describing the purpose of the scatter plot. We create a subset of the data frame containing only fraud transactions. We create a subset of normal transactions, sampling twice as many as fraud cases for clarity. We plot normal transactions as semi-transparent blue dots with smaller size. We plot fraud transactions as red dots with higher opacity and slightly larger size to stand out. We label the x-axis to indicate the time of transactions in seconds from the first transaction. We label the y-axis to indicate the transaction amount. We add a legend to distinguish between normal and fraud transaction points. We add a title to the plot to summarize what the visualization shows. We display the plot on screen. Running the cell now. This scatter plot shows transaction amounts over time, with normal transactions in light dots and fraudulent ones highlighted in red. Notice how fraud points often stand out as anomalies, differing in amount or occurring at unusual times, which would be hidden in simple averages. This visualization demonstrates why anomaly detection is crucial for spotting rare but important events like fraud. Can you spot any patterns that make fraud different? There are several ways to detect if something is an outlier. Common approaches to detect anomalies. Some methods include Z-score method, statistical distance. Isolation forest, tree-based model. Local outlier factor, similarity-based. We will try a few of these next. Running the cell now. Which method name sounds the most interesting to you? Let us use a statistical method called Z-score to detect outliers. We add a comment explaining that this code detects outliers in the amount column using the Z-score method. We compute the mean of the amount column. We compute the standard deviation of the amount column. We calculate the Z-score for each amount value by subtracting the mean and dividing by the standard deviation. We create a new column indicating if the absolute Z-score is greater than 3, marking those as outliers. We print the counts of how many values are and aren't outliers. Running the cell now. This output shows the number of transactions classified as outliers using the Z-score method on the amount column. Notice that most values, 280,731, are labeled as non-outliers, false, while about 4,076 exceed the typical threshold of 3 standard deviations and are marked as outliers, true. This highlights how the Z-score helps detect extreme anomalies by quantifying statistical distance from the mean. Practice: change the threshold to 2 to see what happens. Let us try a popular tree-based algorithm named isolation forest. This is a comment explaining that isolation forest is used for anomaly detection. We import the isolation forest model from Sklern. We instantiate the isolation forest model with 100 trees and a fixed random state for reproducibility. We select the amount and time columns from the data frame as input features for the model. We fit the isolation forest model on the features and predict outliers for each row. We create a new column ISO_outlier in the data frame where true indicates an outlier. We print the count of normal points and outliers in the data frame. Running the cell now. The output shows the count of normal points versus anomalies detected by the isolation forest model, with about 51,676 data points labeled as outliers. Notice the large class imbalance. Most transactions are considered normal, which aligns with the intent to flag only unusual patterns in the amount and time features. This demonstrates isolation forest's effectiveness in isolating rare anomalies within a large dataset. How many anomalies did the model flag this time? Now we will test the local outlier factor, which compares each point to its neighbors. This comment describes that we are using local outlier factor for detecting anomalies. We import the local outlier factor class from the Sklern library. We create a local outlier factor model with 20 neighbors for detection. We fit the model on the feature data and mark rows predicted as outliers in the data frame. We print the counts of outlier and non-outlier labels detected by LOF. Running the cell now. This output shows the count of normal points versus anomalies detected by the local outlier factor method, with about 4,114 outliers identified among 284,807 samples. Notice the class imbalance, which is typical in anomaly detection, reinforcing that LOF flags a small fraction of points as anomalous based on their local density. This aligns with our lesson's aim to explore methods that identify unusual data patterns effectively. Try changing the number of neighbors from 20 to 10 for a challenge. Let us check how many of our flagged outliers were actually fraud. We are comparing the overlap between detected outliers and true fraud cases. This line prints how many transactions flagged by the Z-score method were actually frauds. This line prints how many transactions flagged by the isolation forest method were actually frauds. This line prints how many transactions flagged by the local outlier factor method were actually frauds. Running the cell now. This output shows how many anomalies each method flagged, split by true class, fraud equals 1, non-fraud equals 0. Notice that the isolation forest detects many more outliers overall, including more true frauds, 169, while Z-score and LOF flag fewer total points and fewer frauds. This comparison highlights the trade-offs between sensitivity and specificity in different anomaly detection approaches. Which method seems most useful for this dataset? Let us talk about what these results mean and their limits. Interpreting results and limitations. No method gets perfect results on its own. Some anomalies are not fraud, and some fraud might not look odd to a model. Always check results by exploring and plotting. Running the cell now. Why do you think some frauds might not stand out as outliers? Let us look at a real outlier found by the model and see its details. This is a mini-project for manually inspecting a randomly selected flagged outlier. We select one random row from the data frame where the isolation forest has flagged an outlier, using a fixed random seed for reproducibility. We display key columns of this randomly selected outlier to examine its features and compare the results from different outlier detection methods. Running the cell now. This output shows a single random transaction flagged by the isolation forest method, ISO_outlier is true, but it is not flagged by the Z-score or LOF methods, nor is it labeled as fraud, class is 0. This highlights that different detection methods may identify different anomalies and that flagged outliers are not always fraudulent, reinforcing the need for careful interpretation and manual review. Try finding another random example by changing the random_state number. Some tips to use when hunting for anomalies in any dataset. Best practices for anomaly detection. Normalize features before using algorithms. Use several models to spot different types of oddities. Always combine with expert review when possible. Watch for class imbalance, as rare events are easily missed. Running the cell now. What practice do you think would help you the most for your projects? Let us briefly show how to normalize features with standard scalar. This comment explains that we are using standard scalar to normalize features. We import standard scalar from sklern preprocessing to scale features. We create an instance of standard scalar called scalar. We fit the scalar to the amount and time columns of df and transform these features. We print the means of the scaled features to check they are close to 0. We print the standard deviations of the scaled features to check they are close to 1. Running the cell now. This output confirms that the amount and times features have been properly normalized, with means near 0 and standard deviations exactly 1. Normalizing ensures features contribute equally to anomaly detection models, preventing bias due to scale differences. This step is crucial for improving model reliability when spotting rare anomalies across varied data ranges. Practice: try using scaled features in isolation forest. Let us interact. Enter a made-up amount to test if the z-score rule sees it as an outlier. This is a comment explaining the challenge of predicting if an amount is an outlier. We ask the user to enter a transaction amount and convert it to a float. We calculate the z-score of the entered amount using the known mean and standard deviation. We check if the absolute value of the z-score is greater than 3 to identify outliers. If the condition is true, we print a message that this amount may be an outlier. Otherwise, we print a message stating the amount looks normal. Running the cell now. This output shows the prediction from a simple z-score check on a user-entered transaction amount, signaling it as a potential outlier when the z-score exceeds 3. Notice how the code normalizes the input by centering and scaling it with the mean and standard deviation, aligning with the lesson's emphasis on feature normalization. This approach helps quickly flag unusual values but should be combined with other models and expert review for reliable anomaly detection. Try using different amounts, very high, very low, and something average. If this lesson helped, consider subscribing and sharing with a friend to help them learn too. Let us sum up what you have learned this week. Recap, Week 10 at a glance. You learned what anomalies and outliers are in data mining. You practiced with the credit card fraud dataset. You tried several detection methods: z-score, isolation forest, local outlier factor. You saw that no single method is perfect, always check and combine results. Keep experimenting and discovering hidden signals in data. Running the cell now. Ready for more practice? Go back and try changing parameters to see what changes. Thank you for learning with me this week. Thanks for joining Week 10. If you enjoyed this session, please like, subscribe, and comment with your favorite outlier story. See you next week for more data mining fun. Running the cell now. Invite a friend for next week's lesson and keep practicing.